Okay. Yes, you've been given a sheet that has some practice questions on it and a few notes to guide. The section we're covering and working on today is called Applied Calculus. It's where we take all of our knowledge about calculus, we use it to solve problems that are closer to real-life situations or that involve real-life situations. Many times they call it optimization. Okay. Now, to make something optimum means to make it the best it can possibly be. If you have to produce some goods, it is optimum to probably produce those goods for as cheaply as you can, but to sell them for as much as you can. If you have a limited amount of material that's going into something, you want to use that material as well as possible. This is what optimization means, that we get the best out of a situation as possible. Whenever we go into these situations, there are usually two variables that we have to work with. We end up working with an input variable and an output variable, and maybe those words are similar to you, especially if you're doing physics. And it's one of the key things that we need to do first whenever we go into these situations to end up, to make sure we know which is our input, which is our output variable, then understand how they relate to each other, and then to be able to find what value of our input variable is going to lead to the best outcome from our output variable. Let's have a look at a simple example that explains the process of optimization. Not all your exam questions will be this simple, but this is a good way just to outline the process of solving optimization problems, that then we can take this process and use it to solve even more complex problems like we'll get in our exam. Okay, so let's imagine a situation where we have a rectangle. Right, we've labeled it rectangle A, B, C, D on the board, even though, okay, do you see the position of A, B, D, and C? That's uncommon. Normally we put them in alphabetical order, going A, B, C, D. That's just a slight error there, never mind about that. Okay, won't affect us too much for what we want to do. The condition for this rectangle existing is it has to have a perimeter of 60 centimeters. Imagine yourself having a piece of string 60 centimeters long, and you have to move that string into a rectangle, into the shape of a rectangle. Now, what different types of rectangle could we have, right? Your rectangle will obviously have a width, will have a width and a length. We could have a rectangle with a shorter width, but quite a long length. It could have a much longer width and a short length. The more string you would use up for the base of the rectangle, the less string there is to use for the height. So as you change the width of your rectangle, it would affect the shape of the rectangle. Okay, can we see that from the diagram, how the width will change the total shape? Because what is the condition? The condition is the perimeter has to remain 60 centimeters. Right. Is this picture of having a piece of string 60 centimeters long that makes a rectangle and seeing that, well, if I have a short base, then I'm going to have a tall rectangle. If I have a long base, I'm going to have a short rectangle. Hopefully that makes sense. Right. Now we see as we change the width, do you see the perimeter does not change? It's constant. That's been stated from the question. But what is changing? The area, okay, the area of the rectangle. Now we notice that when the width is really small, okay, we see we've got a certain value, 70-something, area of 70-something square units, when the width is 2.7. As we increase the width, what's happening to the area? It's increasing. It gets to a certain point where it hits what looks like the highest it's going to go, but now as the width increases, it starts decreasing, doesn't it? Okay. So that is what optimization would ask you. What width of this rectangle would give you the highest area possible? From this diagram, I think it's easy to see. Okay, what width when was the area the biggest? Okay, let's see, it gets a maximum, the area gets closer to, let's see, okay, getting closer and closer. Okay, 225. Now if it starts going smaller, now we see it starts getting less than 225. So just from this diagram, what do we see? We see that the area of this triangle is maximized, made as big as possible when the width is what measurement? Okay, so It says here, find the dimensions that will maximize the area of rectangle ABCD. Now, is the answer to this question 225? Yes or no? No, it's not. Let's look carefully. What does it say? It says, find the dimensions. What are the dimensions? The width and the length, the side measurements. Okay. So that's another thing we just need to focus on this question. What are they asking for? Are they asking for what is the optimal result of this problem? Or are they asking you what value input will give you that optimal result? Okay, so here this question is asking you what input value for the width will give you the biggest possible area. So the answer to this question is actually 15. Okay, if the answer to this question was 225, let's say the answer to this question was 225, what would the question have been? Yes. Given a rectangle with a perimeter of 60 centimeters, what is the maximum area that this rectangle could have? Okay, that's what the question would be. Right. Now, what we could do if we had to solve this mathematically, we've had a look at it graphically. We understand what we're doing graphically, but now we want to understand what is the process we follow mathematically with this question, and then we want to take that process and then solve more complex questions, because the questions you get in an exam will be much more complex than this. Okay. If you have a look on the sheet that you have in front of you, on page 1, there are some steps that we're given. Okay. And they look like this. Right. The end result of an optimization question is when we have to identify the max and the minima points. Now, when I say the max and the minima point, that includes both the input value and the output value, the pair of those values, yeah, that would lead to a maximized solution or a minimized solution. Yeah. But to get to that step number 5, there are first a few prior steps that we need to follow. The first one we want to go to is to identify the variable to be optimized and the input variable. In the case here, look at the example question that you have in your sheet. Okay, let's go to that. We're given an example question. Okay, the example question says, a rectangle has a perimeter of 60 centimeters. Let the width equal W and the length equal L. Find the value of W that will maximize the area of the rectangle. Step number 1 is you need to identify the variable to be optimized and the input variable. So for step number 1, what are we wanting to optimize in this question? Okay? The area of the rectangle. What is the input variable that will affect the area of this? It's the width, W. Okay, so step number 1, it says, the question says maximize the area. The variable that has that phrase just before it, maximize the whatever it is, minimize the whatever it is, find the optimum, whatever it is. Whatever follows that is usually the output variable, the one that you're trying to optimize. Okay? And the question also says to find the value of W that will maximize. So when they say find a certain value that will maximize, that variable is usually the input variable. Okay. Now step number 2 is use the information that we have from the question to set up an equation. Okay. So the variable we're wanting to optimize is the area of the rectangle. Okay, let's call it A, capital A for area. And that is a function of W, the width. And we know that in any rectangle, the width times the length would give you a formula for the area. Okay, so that's step number 2 done. Step number 3 is often the most complex part of this question. Okay, is you want to get to a point where the equation the optimization equation only has a single input variable. Here we see, what's the problem with the equation here? It's got a W and an L. So we need to rewrite that L in terms of the W. Okay. What other information were we given about this? We were told that the perimeter was 60. Okay. So we could use that to set up an equation that could isolate the value of L in terms of W. And that will allow us to substitute it into our second equation. Okay. So with perimeter, we know that the perimeter would be W plus W plus L again, and that would equal 60. So 2W plus 2L equals 60. Isolating L, we would get L is equal to 30 minus W. Now with the original equation that you had, where the area as a function of W equals W times L, we can now substitute the L with the 30 minus W, and we now have an equation with the output variable in terms of the input variable where you only see one variable, the input variable. Now we have that stage. Now, in order to optimize, we're going to have to differentiate it. Okay. And that's finding A prime W. Differentiating 30W becomes 30, differentiating negative W squared becomes negative 2W. To find the maxima or the minima value, we have to set that differentiated equation against to 0. Because you know, in the shape of a graph, as it goes up and hits a maximum, curves and comes down, where that gradient is completely flat, where the gradient is 0, is where you will find the maxima or the minima point. Okay. In this case, we solve this simple equation and we get the value of W equals 15. Again, if the question had asked, what is the maximum area of this rectangle, our answer would have been 225. And how would we get that 225 if we needed to? Yes, we would substitute this 15 into which equation? Yes, A as a function of W equals 30 minus W squared. So we would take this here and you would substitute it, in for W. Okay, yes, now what we're going to do is we're going to try work together on some more complex exam questions. We're going to have a chance for you guys to follow this process step by step on some exam questions which are considerably more challenging than this, but you'll see how if you follow the same process, it can break it down into much more simple steps. Okay, guys, we're ready to have a go. Okay, you have this sheet in front of you. You will find, I think the first question that we'll look at, okay, is on page 3. Okay, it's on page 3. If you've got a triangle, a triangular prism that looks something like the diagram that should appear very shortly. Right, okay. Yes, so we have a look. It's on page 3. We're having this question over here. All right. We're going to try, I would like you to have a look, okay, at this question. Before we even begin, I want you guys to understand the idea of scaffolding. What scaffolding is, it's something that examiners do to actually make an exam question more manageable. Okay. Now, you'll notice that question is broken down into a few different parts on your sheet. Okay, there we go. You see, 9.1 says show that y equals whatever y equals to. 9.2 says hence show that the volume of the prism can be expressed at. And then 9.3 says determine the value of x for which the volume of the prism will be a maximum. Okay. Now, what that 9.1 and 9.2 do is helping you do. It's helping you do these 5 steps that you're shown on the front. It's giving you some guidance through those steps. But if we really wanted to challenge yourselves, I feel what you could do is you could actually cross out 9.1 and 9.2. What we should be able to do as mathematicians, be able to cross out 9.1, cross out 9.2, and then focus just on 9.3, and then understand how would we navigate this problem to get to 9.3. Okay, let's just do that verbally together. So, pretend you can't see 9.1, pretend you can't see 9.2. Let's just look at 9.3. It says, determine the value of x for which the volume of the prism will be a maximum. So when we do this question together, I want to try and do it without looking at 9.1 and 9.2 so that we can get a broad understanding of following this process through. Let's talk about it step by step. Let's read the question. Let's try and identify the variable to be optimized and the key input variable. Let's go. Okay, so question 9 says, the diagram below shows a solid triangular prism. The triangle is right-angled with a height of 8x meters, a base of 15x meters, and a hypotenuse of 17x meters, as indicated on the diagram. The length of the prism is y meters, and the total surface area of the prism is 5,760 meters squared. If we read the question, the first one says, show that y equals, and you need to find y in terms of x. 9.2 says, hence show that, but if you look at 9.3, it says, determine the value of x for which the volume of the prism will be a maximum. Okay, so what is the variable that we're trying to optimize here, that we're trying to make as big as possible? X. No. X is the input value. Okay. X is what we change to affect the other variable. So if we make x bigger or smaller, that is going to change something else. Have a look here. So if we can visualize this triangle, try and visualize this prism here. If I had two versions of this triangular prism, one with a small value of x and another one with a much larger value of x, how would the two different shapes differ from each other? What would they look like? Okay. Yes, and the volume of the shape would be affected. Okay. Now, this is a scale model of that particular diagram. We can see that as x changes, now it's got a constant surface area, right? So as x gets bigger, it's not just going to get, the volume is not going to increase indefinitely. We're either going to have a short, fat triangular prism or a long, thin one. Yeah. So as x changes, what happens to the shape? We either get a short, like a shorter but taller prism. As x gets smaller, the surface area has to stay constant. So as that front-facing triangle gets smaller, what happens to the shape as a whole? It gets longer because the surface area has to stay the same. But what will be changing? The volume. Okay, let's imagine you could fill this thing with water. Okay, do you think this shape could hold as much water as that? Which one looks like it could just hold more water? This one. But now we start, oh, okay, look how thin. Yeah, it's really tall, but look how thin this shape is now. Can't hold that much water. So the volume, the amount of water, now we're just using this phrase of water to imagine, to visualize this. Okay, the amount of water that this shape could hold at the moment is quite small. It increases, 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 but now we would imagine the volume of water would start decreasing again. Okay? And now that would hold a lot less. So for some value of x, we don't quite know where, but for some value of x, that shape with the constant surface area would hold as much water as it possibly can. So when we look at this question, 9.3 says, determine the value of x for which the volume of the prism will be a maximum. So when they say, determine the value of x for which the volume will be a maximum, they say that volume will be a maximum. What's being maximized? Volume of the shape. We want to get the volume of the shape as big as possible. What's the input variable that affects the volume? X. So we want a formula that has volume equals and a series of calculations on x. That's what we want. Okay. Once we've got that, we could differentiate it. Once differentiated, set it equal to 0 to find the maximum, and then we'll get that value of x that makes it as big as possible. Let's have a go. Okay, now there's a bit of algebra that we've got to get done first. So we're not going to follow 9.1 and 9.2. Right. We are going to follow those steps that we got in the beginning of this sheet. We are aiming for 9.3. What's step 1? Okay, to identify what we want to optimize, and that's the volume. Okay, so we want to identify the volume. Okay, and that volume is going to be a function of x. So when x changes, the volume will change. Right. How would we calculate the volume of this shape over here? Volume of a prism. Can we think back to grade 9? Do we remember how we do that? We see it's got a constant cross-section and a length. So we get the area of the cross-section and multiply it by the length. That will give us the volume of the shape. So it's the area of the triangle in front multiplied by the length. How would we calculate the area of the triangle in front? Half times base times height, right? Half times 15x times 8x. But then we have to times it by the length, which in this case is y. Right? So let's have a look at this formula. Let's simplify it as far as we can. The volume as a function of x would be, let's say, a half times the even number, half times 8, 4. 4 times 15 is 60. It would be 60. X times x, x squared times y. That's as far as we can get with this formula so far. What is the problem now? 60, oh, right. Okay, now I appreciate that, guys. 60x squared y. Now, step 1 says identify the variables. We did that in our first line. And now step number 2, we've set up the formula. We've got the formula. Now, step number 3 says we've got to simplify it to the point where we only have the input variable. What's the problem here? We don't have the input variable only. We've also got this y. How are we going to solve that problem now? Yes, this is where 9.1 helps us, right? Okay, now I'm just going to steal that value and put it in. Let's actually work it out. What information is going to help us work that out? What information did they give us in the question that will give us a formula with y and x only in it? The surface area, correct. Okay, now, let's just put a line under this for the moment. Okay, the surface area. How will we calculate the surface area? It's the sum of all the faces, isn't it? Okay, the surface area is the sum of all the faces. We have one face at the front, which will be a half times 15x times 8x, but the trick is that one, there are 2 of them. Okay, so we've got this front face sorted out, we got that back face sorted out. Now we've got this one on the side. What is that? That will be 8x, y. Are we happy with that? That this surface on the back here would be 8xy. The height of 8x, the length of y, that rectangular surface at the back would be 8xy. Okay, that's not very clear. The base of this would be 15xy, all right? So we've got the back surface, we've got the base. Now this front diagonal slanted surface, what would that be? 17xy. Let's simplify this as far as we possibly can. Now the first part would be a half times 2 would cancel itself out. So 15 times 8, let's get that, what would that be? 1.5 times 8, 120, right? 120x squared. Now 8xy plus 15xy plus 11xy, 8, 15, 20, wait, 17, sorry. That looks like an 11. See, these little mistakes can catch you out easily. That's poor writing. 8 plus 15 plus 27, is that 40? So this is what the surface area equals. But we are told that this surface area is equal to the number 5,760, 40xy. And that's equal to 5,760. Yeah. Now what we want to do is we want to isolate y. You can probably, now when solving these questions, when in your exam you're actually solving 9.1, you know what I recommend doing? Look at your work so far and then check back often at what you're supposed to show and see, is it on track? Let's have a look here. Okay, I've got a number 5, 7, 60, 120, and a 40. It looks like I've got all these. It looks like we're on track, so we can carry on working. If it looks like it's way off, then you can go back and check your work. Okay, so we've got y. Now, what does that help us do? Sometimes when we're going through a process, we can forget why we were doing it. What were we trying to do? Okay, we were trying to find this y in our volume formula. We were trying to find that in terms of x. Right. So volume in terms of x equals, now, what I'm going to do, to save time, instead of watching me and then you doing it, I'm going to say you can get your pens out now. What you can do, catch up to where we are now on your paper, and then take a step ahead. Try and substitute in this value of y into your volume formula, and let's simplify it as fast as possible, or as far as possible, and then we can compare how we did that together. Yeah, so that's where we are. We have our volume formula, and what we're wanting to do is to substitute in for y, the value of y in terms of x that we discovered earlier. Okay, so what phase of the process are we working through now? Okay, we're working through the simplifying stage. Okay, that on your notes there was number 3, where it says simplify the equation to the point where only the input variable is seen on the right-hand side of the equation. Sometimes you will need to substitute from a second equation, and that's the part. That's substituting from the second equation. That's where we are now. Okay, so I'm going to give you a chance without. I've purposely covered up what I wrote earlier, because I want you to do it not from memory. I want you to do it from understanding now. Okay, if you've gotten to the point where you think, oh wait, what did I do? What did we do here? Don't copy. You can ask someone. Just give a point. Oh, why did we do this? And just try and get to this point. And what I want you to try and get, where I want you to try and get to by yourselves, is to the point where we have only x in this formula now. I'll give you 5 minutes. Even if we don't finish completely, 5 minutes to try and get that far on yourself. So you're exercising your own thinking there. There's a small tip I would like to give at this point when simplifying in these brackets. For this type of expression, we know that we're going to have to differentiate it. Do we ever want to have to differentiate something where you have a fraction and there's more than one term in the numerator? No, we don't. So if we have a look at this expression here, we've got 2 unlike terms in the numerator of a fraction. Yeah, we don't want to have to differentiate it like that, not in grade 12. You can take the 60x squared and distribute it to each term in the numerator. You can do that, all right? Or you can separate the fraction first and then distribute the 60x squared in. Okay, so you can do it like this. You could keep the 60x squared on the outside, and here you've got 5, 7, 60 over 40x minus 120x squared over 40x. Okay, and then distribute the 60x squared. That might be a small change to your way of doing it that could help. Right. If you are quite happy with distributing the 60 in and then separating them later, no problem at all. Okay, let's get to the point. So with your calculators, you could do 60x squared times 5, 7, 60. And what do we get when we do that? Sorry? 60 times 5, 7, 60? 3, 4? 3, 4, 5, 6? Okay. Is that correct? Sorry, you're saying it so fast. My brain works slower than that. Okay, minus, and then 60 times 120, is that 7,200? That will be x to the 4 over 40x. Do you remember the x squared? Timesing the x squared will make that x to the 4. Okay, and this is where we can use our nice calculators to, oh, I forgot that 40. That would be a big mistake. All these little things that could catch you out. The one nice thing about this question is, remember, when you, in an actual exam, when you look back, they're telling you what you're supposed to arrive at. So if I'd made that silly mistake of just forgetting to write the 40 from one line to the next, and if you get an answer that's completely different, it gives you the opportunity to go back and have a look. You won't have to work out, is your answer right or wrong? You'll know. Okay, guys, x squared over x would leave you with just an x, and simplifying that with your calculator, you'll just get your 8,640. And x to the 4 over x would leave you with an x cubed. 7,200 over 40 would give you your 180. Now, I didn't calculate those myself. I just realized there's only one step left. And I just looked at the question again to see the answer that I should arrive at, something that in an exam can help you. Okay, so guys, now what you have is you have volume as a function of x, right? Now, let's have a look. What were we wanting to do? We want to find the value of x. Remember, there's some value of x that will make this shape have the highest volume possible. Okay. Let's try and find that value of x. How do we do that? Now we're on to step, which number step? Okay. We're on step number 4, where it says differentiate with respect to the input variable. So let's do that. What would it be over here? The v prime x would be 8,640 minus 180 x squared. Okay. Now, if we set that equal to 0, we find the value of x that would maximize the volume. Sorry? Timesing by the 3, of course. Next time I'll definitely bring my sweets. Okay, so we get 16. Okay, yes, now we know if x squared equals 16, the square root of 16 could be positive or negative 4, but in this situation, does it make sense to consider the negative 4 solution? No, because we can't have negative units of length, okay, in this. So let's go back to this diagram and have a look. Okay, what did we notice? The volume here looks pretty small for small values of x. As x gets bigger, the volume really looks small. Like that's such a thin prism that it hardly looks like anything. Let's see, when does it get to its maximum? It looks like, according to our calculation, that there would be the type of shape that would give us the biggest volume. Okay, so hopefully that's helped visualize and break down the process. Reviewing this question. Yes, we didn't look at 9.1 and 9.2, but the approach we've taken, okay, step 1, okay, was here, step 2, and step 3, step 4 was finding Step 4 was the differentiating. So just that there was step 4. Setting equal to 0 and getting the value, that was our step 5. So you see, guys, without even being given 9.1 and 9.2, these steps could help you navigate through a whole question to get to the end result. But in many exam questions, you will get that scaffolding. They will ask you 9.1, 9.2, 9.3, and give it to you step by step. But now, hopefully, when doing those questions, you'll be able to know, where's this going? How are we going to use it in the next phase? Okay. Guys, for a remainder of the time, I would like to give you a question that would require you just to think a bit differently. Okay. What we're going to do for the last 10 or so minutes that we have, we might not be able to work through and solve this whole question, but we're going to outline how we would use the 5-step process to go about solving this question. Okay? Because there are a few little curveballs here, but maybe you won't find them curveballs. Let's have a look. Yes? So this you'll find on page 2, on the top of page 2. Okay. So it says the diagram below shows triangle ABC drawn such that its vertices lie on rectangle PBQS. As shown, PA equals SC equals T. PB equals 12 and BQ equals 7. So you have a rectangle, a constant base of 12, constant height of 7, but within this rectangle there is a triangle drawn where the vertices touch the sides of the triangle. Right. Now you see, it doesn't give you 9.1 or 9.2 and everything, it just says, calculate the smallest possible area of the triangle. Okay, so step 1, what is the variable that you're wanting to optimize? The area, yes. You're wanting to, it says the smallest, so you actually want to find the minimum value. You want to minimize the area of triangle ABC, the value of the area, if you change this input variable. T, correct. Okay, so let's visualize this. Let's have a look at what's actually happening here. Right, you have this triangle, PSQB, all right, and you have this value of T. The value of T, of course, wherever you see T, it'll have the same value. So PA will always equal SC. Now, as I minimize that value of T, we see the area of the triangle is increasing. It's getting bigger. As T increases, the area of the triangle decreases. You can get it smaller and smaller and smaller. But as you guess it, after a certain point, that area starts to increase. Here it's 24.57. And if you decrease T again, it's 24.1. Now we could probably guess, even though the calculations aren't rounded very accurately, the way this is set up at the moment, you could probably guess what the smallest area would be. It looks like it's going to be 24. And if we had to guess what actually causes, what is the length of T that actually causes that, we might be able to do it graphically. But this here is just to visualize what happens. So as the value of T increases, it affects the area of the triangle inside that square. So going back to our piece of paper, we've identified the two variables. It's the area of the triangle as a function of T. Okay. Now, the problem here is, how on earth would you get a formula for the area of the triangle? Sorry? The sides of the triangle. Okay. Now, if we have a look, we wanted to get the side lengths of the triangle. Once you've got all the side lengths of the triangle, what would you do with that? Sorry? Now, the triangle when you okay, so to get each side length, you could look at the theorem of Pythagoras, yes, to get the side length. But now you've got an expression for each side length of the triangle. Then what's our next step? What calculation would you do to calculate the area? Sorry? Sine rule? Okay, cosine. It may get complicated. It may get complicated. And what's complicating this is that we are focusing directly on the gray shaded triangle. But what if we viewed this question that, right, if we have this rectangle here, and if we minused from it this piece at the top, minus from it that one at the bottom, minus this one on the left. So you see you've got piece number 1, 2, and 3. Piece number 1, 2, and 3. What if we worked out the area of each of these triangles 1, 2, and 3 and subtracted it from the product of 12 and 7? Okay, that then would give you the area of the actual shaded triangle with a little less headache. Okay. Yes? How about we try this? Okay. What we've got now is we've got a bit of time, I think, before your next session begins. Okay. How about we use those steps that we've got, do a bit of independent work. That's all I'm going to say for this one. Now I can say over to you. Welcome to discuss this question with people and work together on it. We'll have a look. I will try and show you a solution to this question. Okay, I've got the worked solution for it, but let's see how far you can get up until the next session starts. Okay, yes, over to you. Let's have a go.